We will now do some exercises. First one, V Hilbert and dA, sorry, A from dA contained in V to V densely defined and closed. So, if it is densely defined, you can define the adjoint, and since V is a real Hilbert space, we always deal with real unless otherwise mentioned. So, we can, or even complex, it does not matter, but in this case real. We can define the adjoint from V into V itself. Okay. So, then A star is densely defined. We know that whatever may be A star is always closed. If A is densely defined and closed, then A star is also densely defined and closed. Okay. So, solution. So, so let VW equal to 0 for all W in D of A star. So, we want to show, so to show V equal to 0. So, this is the Hahn-Banach theorem method of showing something is dense. So, we have dA star which is a subspace, and if you want to show it is dense, you have to take a vector V which, or a functional, in which case by the Riesz representation theorem it is just the inner product with a vector, and therefore we have to show that this is equal to 0. So, if not, V is not equal to 0, then you have that 0 V does not belong to the graph of A, because graph of A is what U is in domain of A. If the first component is 0, the second component must forcibly be 0. So, if V is not 0, this cannot be the graph of A, and graph of A is closed, that is given here. That is the hypothesis, the graph of A is closed. Therefore, you have a closed subspace of V cross V, and you have a vector which is not in it, and therefore by the Hahn-Banach, there exists xy in V cross V such that so y acting on V inner product. So, there exists a pair xy in V cross V. Here this is the inner product. Okay. This is equal to 0, not equal to 0, and x u plus y a u equal to 0 for all u in dA. That means xy annihilates all the elements of the graph. So, you have a continuous linear functional which is again a pair of elements in V cross V such that it should not vanish on 0 V. So, yv is not equal to 0, and it vanishes on all the elements of the graph, that means x cube plus. But this implies that mod yau is less than or equal to norm x norm u, and this implies that y belongs to the domain of A star by definition, and that implies that Vy has to be equal to 0, because that is the definition of V here, and but that is a contradiction because we know that Vy is not 0, and therefore, so this implies that V equal to 0, that is D of A star dense. A 2 by 2 complex matrix with distinct eigenvalues. Find alpha beta such that e power A is actually alpha times I plus beta times A. So, solution. So, let A equals lambda 1 0 0 lambda 2. So, this diagonal matrix with distinct. So, lambda 1 not equal to lambda 2. Okay. So, then what is e power a? E power a, if you compute, this is nothing but e power lambda 1 0 0 e power lambda 2. Okay. This is just straightforward calculation, I plus a square by 2 factorial etc. If you compute, so you will get precisely this thing here. So, now you want this to be equal to alpha I plus beta a. Okay. So, then you have e power lambda 1 should be alpha plus beta lambda 1, and e power lambda 2 should be equal to alpha plus beta lambda 2. So, if you saw, and lambda 1 is not equal to lambda 2. Therefore, if you solve this pair of equations, you will get beta, if you subtract, you will get beta equals e power lambda 1 minus e power lambda 2 by lambda 1 minus lambda 2, and alpha equal to lambda 1 e power lambda 2 minus lambda 2 e power lambda 1 by lambda 1 minus lambda 2. Now, if A has distinct eigenvalues, lambda 1 not equal to lambda 2, then A can be written as P inverse dP, where D is the diagonal matrix lambda 1 0 0 lambda 2. So, this is, you can diagonalize the matrix using eigenvectors. Then what is e power a? Then e power a is nothing but, if you do the calculation, it will be P inverse e power d P, and that is equal to P inverse alpha I plus beta d times P, because when you take a square, it is P inverse dP, P inverse dP, P inverse will cancel, you will get P inverse d square P. Similarly, a cubed, a power 4 and so on, and therefore e power a is nothing but P inverse e power dP, and this is equal to this, and that is equal to alpha times identity plus beta times P inverse dP, since P inverse dP equal to a. Okay. So, it is the same constant. So, you have what you do for the diagonal serves for all the matrix also. So, 3, let alpha omega belong to R and A be the matrix alpha omega omega alpha, sorry, alpha minus omega omega alpha. Then show that e power T A is nothing but e power alpha t times cos omega t minus sin omega t sin omega t cos omega. So, solution. So, A can be written as alpha times identity plus 0 minus omega omega 0. Okay. So, if you took e power T A, now e power T alpha times Ti, so this is sum of two matrices, they commute because one of them is identity, and therefore e power, this will be e power alpha I e power b Tb, where b is equal to 0 minus omega omega 0. But e power alpha I is nothing but e power alpha t times I. So that is e power alpha t times e power Tb. Okay. So now you have, what are the eigenvalues of this matrix? So if you compute the eigenvalues of this matrix, they are what? So lambda square minus trace is 0 plus determinant, so that will give you plus omega square equal to 0. So lambda equals plus or minus I omega. So then if you compute the constants, then you know that then you can write B is equal to e power B, sorry, is equal to cos omega t plus 1 by omega t sin omega t times B. Okay, just so this is apply exercise 2. Okay, and then you will get whatever you want. Okay, so if you from this you should be able to complete this exercise. Okay, 4. So S of t greater or equal to 0, C0 semi group in a Banach space, on a Banach space. So what do you mean by exponentially stable? That means there exists m and omega positive such that norm of St is less than or equal to m e power minus omega t. Okay, this is then it decays exponentially, the norm. So show that St is exponentially stable if and only if there exists T naught positive such that norm of St naught is strictly less than 1. So this is a very beautiful characterization. So if you have one element of the semi group which has a norm strictly less than 1, then the semi group norms decrease exponentially. Okay, so if solution, so St t greater or equal to 0 exponentially stable, that means norm St is less than or equal to m e power minus omega t for omega positive. Okay. So this implies there exists a t sufficiently large such that norm of St is less than 1. Okay. For the, in fact, norm of St is less than 1 for all t greater or equal to capital T. Okay. So then trivially, so conversely, let T naught be greater than 0 with norm St naught strictly less than 1. Okay. Then norm of S delta is less than or equal to some A for all delta 0 less than or equal to delta less than or equal to T naught, because you know there exists omega naught greater or equal to 0 and m naught such that norm of St is less than or equal to m naught e power omega naught t for all t. Okay, given any semi group you have this, and therefore if you put this increasing function, exponential monotonically increasing function, therefore for all t less than or equal to T naught, you have norm of St is less than or equal to m naught e power omega naught T naught, which is I call as A. Okay, so we have some elements here. Okay, so now you have that log norm of St naught is negative because St naught is less than 1. Okay, so now you put omega greater or equal to 0, omega positive, sorry, equals minus 1 by T naught log norm St naught. So this will be positive. Okay, so norm of S delta for all 0 less than equal to T naught, delta less than T naught. Norm of S delta is less than equal to A, which is equal to A e power omega T naught e power minus omega T naught. Okay. Now, delta is less than T naught. So, omega delta minus omega delta will be greater than minus omega T naught. So, e power minus omega delta will be greater than e power minus omega T naught. Okay. So, this is less than or equal to A e power omega T naught e power minus omega delta. Now, given any t in R, t greater than 0, we can write t as n times T naught plus delta, where 0 less than or equal to delta less than T naught, the usual trick which we did later on. So, S of t by the semi group property is S of T naught power n times S of delta. Okay. Now, therefore, norm of St is less than or equal to norm of S of T naught power n into norm of S delta. Norm of S T naught power n is equal to e power where is the definition of omega here. Norm of S T naught power n is e power minus n T naught. Okay. And norm of S delta is less than or equal to A e power omega T naught, okay, times e power minus omega delta. So, this is equal to m. So, m is equal to A e power omega T naught and then e power minus n T naught n omega T naught. Omega times n T naught and e power minus omega delta, which is equal to m e power minus omega t. Okay. So, that proves the exponential decay. Let C belong to R, C naught equal to 0. Let U naught belong to H2 of 0 1 intersection H1 0 of 0 1. Show that there exists a unique solution of du by dt minus d2u by dx square plus c du by dx equal to 0, 0 less than x less than 1, t positive, u of 0t equals u of 1t equal to 0 for all t positive, and then u of x0 equals u0 of x. Okay, so solution. So, we set omega equal to 0 1 and we set v equal to L2 of omega, okay, and we define d of a to be H2 of omega intersection H1 0 of omega and set au equals u double dash minus cu dash. So, then what is AUU? U in D of A. So, that is equal to u double dash times u minus c integral u dash u 0 1, okay, and that is equal to minus integral mod u dash square 0 1 dx, okay, and minus c by 2 integral u dash u is u square prime, okay, 0 to 1. Now, if you evaluate this at the end points, sorry, this because it is a prime, and therefore you will get it is 0 at the two end points by the boundary condition, and therefore this term equal to 0, and therefore this is less than or equal to 0. Okay. So, you have that A is a dissipative operator. Now, you look at this AUV equals integral 0 to 1 u dash v dash dx minus C integral u dash v dx plus and plus integral u v dx 0 to 1. So, then AUU in this case is equal to integral mod u dash square 0 to 1 plus C integral 0 to 1 u dash u, again this is 0 by the calculation which we did just now, plus integral u square dx, which is equal to norm u square 1 omega. Okay. And therefore, this is h1 0 omega elliptic. Therefore, for every v f in L2 of omega, there exists a unique u in h1 0 of omega by Lax-Milgram such that integral AUV equals integral FV on omega, that is, and then if you look out what is it is minus u double dash plus cu dash plus u equal to f in omega, u equal to u0 equals u1 equal to 0, and u double dash is equal to cu dash plus u minus f, and that belongs to L2 of omega. So, this implies that u is in h2 of omega intersection h1 0 of omega, which is nothing but d of a. Okay. And what is the differential equation say? I plus I minus au A is what? U double dash minus Cu, okay, Cu dash. Okay, so this implies range of I minus A equal to B. Therefore, A is maximal dissipative, implies there exists a unique solution to star. 6. This is called the Klein-Gordon equation. So, let M belong to R, M not equal to 0, and omega in Rn smooth bounded open set gamma equals d omega. Let f belong to h2 of omega intersection h1 0 of omega and g in h1 0 of omega. Then there exists a unique solution u such that d2u by dt2 minus Laplacian u plus m square u equal to 0 in omega cross 0 infinity, u equal to 0 on gamma cross 0 infinity, u of x 0 equals f of x x in omega and du by dt x 0 equals g of x x in omega, and u belongs to C of 0 infinity with values in H2 of omega intersection H10 of omega intersection C1 of 0 infinity with values in H10 of omega intersection C2 of 0 infinity with values in L2 of omega. So, we set du by dt equal to V, and then you get dV by dt equals Laplacian u minus m square u. So, you said V is equal to, like in the wave equation, H10 omega cross L2 of omega, and dA equals H2 of omega intersection H10 of omega cross H10 of omega, and you write A of u is equal to V and delta u minus m square. Okay, so u equals ub. Okay, in dA. And now you consider V1 V2 equals integral, so rather u1 u2 inner product I am going to define as integral on omega grad u1 grad u2 plus m square integral omega u1 u2 plus integral omega v1 v2. So, u1 equals u1 v1 and u2 equals u2 v2. Okay, so this is in L2 and this is in H10 intersection H2. Okay, so then this is this defines an inner product equivalent to usual inner product on H10 of omega cross L2 of omega. L2 is the same. So, this you are taking a thing, and you know that the L2 norm is less than the H10 norm by the Poincare inequality, and therefore, this is less than the constant times the usual norm, and the usual norm is of course less than this, and therefore, you have that these two are equivalent. Okay, so, this is the usual inner product which is integral grad u1 grad u2 plus integral v1 v2. Now, AUU in this inner product, new inner product is equal to integral what is A? A is V this. So, you will have grad V dot grad U plus m square integral V U. So, U equals U V in dA, okay, and then plus delta U V minus m square u v. So, these two get cancelled and then these two also get cancelled, and therefore, this is equal to 0. So, now let f belong to H10 of omega and g in L2 of omega. Let me write capital F capital G so that I do not confuse with the initial data given to you. So, we want to show I minus a equal to v. So, we want to solve the following equation. So, find uv in dA, okay. So, such that u minus v equal to capital F and minus Laplacian u plus m square u plus v equal to capital G, and then that will give you, if you add these two, minus Laplacian u plus m square u so m square plus 1 u equals capital F plus G, and then this can always be solved. So, capital F, so this belongs to H10 of omega and this belongs to L2 of omega G, okay. So, this belongs to L2 of omega, implies there exists unique u in H10 of omega solution, and plus regularity implies u belongs to H2 of omega intersection H10 of omega, okay. And now you can write v equal to u minus f, and this belongs to H10 of omega. So, this implies uv belongs to dfa, and it solves the system of equations. So, you have that range of I minus v equal to I minus a equal to v, and this implies there exists unique solution with required properties from general theory, because you have little more than dissipative, you have au of u is equal to 0 in fact, like in the wave equation, and therefore you have this. Okay, so with this I will stop these exercises, and this course has also come to an end. I do hope you did enjoy it and you got something out of it, and that it was a useful learning experience for you. Thank you for your attention.